So Salil is a professor in the School of Computer Science and Engineering at University of New South Wales, Sydney, in Australia. He is also affiliated with the Cybersecurity Cooperative Research Center and the UNSW Institute for Cybersecurity. His research interests span in the domain of Internet of Things, pervasive computing, cybersecurity, blockchain, and applied machine learning. He has published over 300 peer-reviewed articles and is leading several governmental and industry-funded research projects on this topic. So Salil received the Frederick William Bessel Research Award in 2020 and the Humboldt Research Fellowship in 2014, both from the Alexander von Humboldt Foundation in Germany. He is the recipient of 8 Best Paper Awards. Salil has held visiting positions at I2R Singapore, Technical University Darmstadt, University of Zurich, and Graz University of Technology. He is a senior member of the IEEE and ACM distinguished speaker and an IEEE Computer Society distinguished visitor. He served as the editor-in-chief of the Ad hoc Networks Journal and an associate editor of IEEE Transactions on Network and Service Management, Computer Communication, and Pervasive and Mobile Computing journals. He has served as general chair and chair of several IEEE ACM international conferences such as PARCOM, ICBC, IEEE Blockchain, LCN, CNSM, AUMOM, and TWSM. Salil has also co-authored a book titled Blockchain for Cyber-Physical Systems, published by Artec House in 2020. So Salil, over to you.
Thanks, Sandeep, for the warm introduction. Thanks also to Maina for organizing all this. And it's my great pleasure to present some of the work we've been doing. So this work, today I'm focusing on some of the work we've done in the supply chain space. Most of this work was done by my former PhD student, Sidra. She's now, actually, I should change her affiliation. She's now working with CSIRO's Data 61 as a postdoc. And then we've some collaborators from QUT and Data 61. So very briefly, I mean, all of us are aware of supply chains. I mean, pretty much anything that you buy, be it from a physical store or an online store, has been sourced through a supply chain, right? So they're pretty complex, they're pretty global, and we are actually feeling the pinch right now. In many parts of the world, we are experiencing problems due to supply chain issues. Sourcing of goods has been a problem due to certain things going on in the world. So this has created a lot of pressure on supply chains, and we are seeing that translated into high prices of various things, right? Now, we've talked to a lot of people working in the supply chain industry, and unfortunately, the way things are managed there are quite primitive in some instances. So the digitization of supply chains hasn't, it's happened to some extent, but there's still a lot of scope to improve that, right? So some things that we think, as computer scientists, we might think, okay, these are few things that are quite obvious to digitize, but often it's very hard to do that in these complex systems. So of course, this will continue. It has happened. It will keep happening, right? Now, one thing that is particularly interesting in supply chains and quite relevant and important is this whole issue of traceability. So I'll kind of use food as an example in most of this talk, but the ideas I present can apply to any kind of goods. So with food particularly, or any goods really, there's always this whole issue of counterfeiting, right? So particularly with premium products, you can expect some fake products being sold. So that is certainly a challenge for these companies. There are various issues surrounding outbreaks that can happen due to contamination of food products, and it can often take a little while to detect and sort of figure out what actually went wrong in the supply chain. There's a lot of waste, unfortunately, still happening, which is a shame, but that's how things are. So I think having a sort of more insight into supply chains can help us solve some of these problems. And in general, as consumers, we are demanding a lot more. We are demanding to know a lot more about where our food comes from, right? So there's this whole movement of being able to follow the food from your farm to the fork, to the table. And there are some weird things happening in the world. So this was something that happened here in Australia, I think 4 or 5 years ago, where people discovered needles in strawberries, and then everyone stopped buying strawberries, right? So this created a huge loss for all the farmers, and it took them several months to actually figure out who was the culprit. So clearly, it's not like traceability systems do not exist. They are there, out there, but they are often very siloed. They're centralized. The data can be unreliable. And very often, the consumers, the end user, may not necessarily have access to this data. So this is still quite sort of disjointed, right? So we started looking at this a few years ago, and in our group, we were kind of looking at this whole intersection of cyber physical systems and blockchains, and how blockchains could address some of the problems within cyber physical systems. So, of course, we started to think that blockchain could potentially be a solution. And of course, we were not the only people. There were various other companies and research groups looking at this. Now, I don't want to spend a lot of time on sort of giving you a quick intro to blockchain. I would imagine most of the audience would know it, but I'll just spend like like 2 minutes just to sort of give a very high level overview, just in case, right? So, of course, what are blockchains? Well, there are distributed ledgers. So rather than maintaining a ledger at a central entity, you maintain copies across multiple entities who are managing the blockchain. And data is stored in the blockchain in the form of transactions. Now, this can be any sort of data, doesn't have to be cryptocurrency, which is kind of the common example, but it could be any data. So in the context of supply chain, it could perhaps be information about a trade of a particular item, right? So these transactions are grouped into blocks, and then there's a certain consensus algorithm that is run to decide who can add this new block to the blockchain. One of the node wins, and that node then gets the opportunity to add the block in the blockchain. And once sufficient blocks have been added, you can sort of assume that your transaction is now confirmed, and it stays in the blockchain forever. So it's mutable, right? So yeah, this was just a 1 minute sort of overview. I'm skipping all the minor sort of details about this. And broadly speaking, there are sort of two ways to design blockchains. So there's this whole notion of an open blockchain, a permissionless blockchain, right, which is public. Anyone can join. The users are anonymous. And as a result, the various processes involved to manage these blockchains have to be very robust, right? Otherwise, you could create a lot of harm there. So there's this whole proof of work, proof of stake sort of consensus protocols involved there. And examples, of course, are Bitcoin, Ethereum, and so on and so forth. On the other hand, you have what are called permission blockchains. So these are a bit more restrictive. Only certain identified users can join. And as a result, you can have a little more trust in the users. So some of the processes can be sped up, and you don't necessarily need complex consensus algorithms like proof of work, for example. And Hyperledger is a very prime sort of example of this. And then, of course, we have some smart contracts, which are sort of quite critical to most of this work that we've done here. So this is basically just like your paper contract that you might say if you purchase property, you will probably have a paper contract, right? So the only difference here is the contract is embedded into lines of code. And you could sort of set the contract in a way that when certain conditions happen, so for example, certain transactions are executed, then certain sort of rules can be, certain part of the code would be fulfilled, and you can enforce certain actions. For example, it could manifest into a payment in the context of a supply chain application. So blockchain has a lot of benefits that it can offer. So of course, everything stored there is tamper-proof. You get this very nice view into the blockchain, so you can actually search through the blockchain, and you have good transparency into everything that's stored there. And the key point being, you're not relying on a central entity, you're not relying on third parties, right? So this is a inherently distributed system. And that also means you don't necessarily need to trust the entities, because as long as they're following the protocols and assuming the protocols have been implemented correctly, you kind of build trust on top of this untrusted network in a sense. And of course, everything is following the state-of-the-art cryptographic algorithms. And in particular, the use of smart contracts can help a lot in automating various processes. So blockchain can actually bring a lot of benefits to supply chains. So of course, it can give you traceability, clear view into how the products were moved. That can allow you to detect mishandling. It can allow you to detect, say, counterfeit goods and so on and so forth. It can also help on the finance aspect. So assuming typically in supply chains, you would also have some exchange of money, right? So some of this could be automated using smart contracts, and you could even have an underlying sort of cryptocurrency associated with the blockchain, if you may, to manage the payments. It also gives you a possibility to audit. So you can, once you have the data logged on the blockchain, you could have, say, authorized government bodies go and inspect this data and perform all sorts of compliance checks, right, which are quite important in the context of food. You can also do lots of data analytics. So assuming you have sort of information coming in from various parts of the blockchain, say you've got IoT sensors embedded right from the farm all the way to the retailer, then you can get a lot of information, and this can be analyzed to get a lot of insight into how the product was managed within the supply chain. And it can also help with insurance because the fact that the data is immutable, it can then be looked at to determine perhaps liability in the case of something going wrong and so on and so forth. And payments can be automated essentially, so allowing quick payment of benefits in case of losses and so on and so forth. So if you were to sort of look at how most people have used blockchains in the context of supply chains, right? So this is a nice sort of representation of that that we've been using in some of our papers. So you can sort of imagine you have these 4 layers. So you have at the sort of left end here, you have what we call the data layer. So that's where all the data that's associated with the blockchain is coming from. So this could include, as I hinted earlier, various sensors that may be deployed. There could be sensors even embedded in the product itself. You could also have some external inputs coming. So let's say regulators are performing site visits and they're giving you reports, right? So all that data that is going to be used to action some of the applications here is essentially originating there. Now, where does the data get stored, right? You don't necessarily need to store all the data on the blockchain. In fact, you may not want to do that because that will create problems in terms of the size of the blockchain. So typically, you would actually store the data off the chain. This could be existing ERP systems. It could be distributed storage systems like IPFS or even existing databases, right? So, this you could kind of make use of whatever suits your needs. And then here is where the heart of the sort of system is. This is the blockchain layer. So this is where all the transactions get stored, which would contain hashes of any data that's logged here. And you could also implement all sorts of additional functionalities, as you'll see in this talk. So I'll kind of cover this as we move through the talk. And then at the top here, you have the application layer. So this is essentially providing all sorts of interesting applications, right? So once you have all this in place, then the ledger can be queried to implement all sorts of interesting applications, be it data analytics, be it auditing, be it traceability, be it finance or compliance. Okay, so this is depicting the journey we've taken in this particular space. So we started working on this early 2018, where we first focus on just the basic idea of using the blockchain to manage supply chain. So this product chain was the first piece of work we did. Then the second part looked at the issue of trusting the data. So I'll spend a little bit of time talking about TrustChain. I'll very quickly go over product chain because this is kind of just laying the foundations for most of the further work. The scalability part here, I'll actually skip this. I don't want to make this like a 2-hour lecture. So what I might do is after TrustChain, I'll then focus more on the privacy aspects and present 2 things that we've done there. Okay, so product chain, right? So this was our first work looking at how do we sort of set this all up. So again, the idea here was to come up with a full-fledged approach, a holistic approach, where we show how we can actually use blockchains to manage supply chains. So we presented a consortium-based model, which is used to manage this permission blockchain. And we also designed a transaction vocabulary to embed all the information needed at the data layer that I showed you earlier. And to ensure scalability, we kind of employ sharding. Again, I mean, this is not something radically new, but at that time, this was one of the earlier works to propose this. And then the other important thing very important thing with supply chains is managing who can read and write what in the ledger, right? Because remember, in the end, these are companies. They're there to make profits, and there are certain trade secrets that they may not necessarily want to reveal, right? So there's some care has to be taken into the access control aspects of it as well. So this is the high-level overview, if you may, of the system. So we have what we call a governing board, which could be of, say, food control and audit authority, some government associations, and of course the technology vendors deploying all of this. And they come together and define certain consortium rules, which are then, they sort of indicate how the ledger is managed, who can read and write what. And this gets manifested as a access control list and implemented by the technology vendor. And then you have all the participating members who are the entities involved in the supply chain. And then you have the end user, the consumer, who may want to access certain information from the supply chain. So this is just a simple illustration of an access control list, right? So this is indicating what type of members can do what within the blockchain, and so on and so forth. For the architecture, we envision having sidechains, given that blockchains span pretty much the globe. Supply chains span pretty much the globe. So it's unlikely. I mean, the easiest way to scale this is then to define sidechains for different regions, right? And then you kind of have the sidechains maintaining their own blockchains. You can have various participants attached to these sidechains. And you can define certain membership sort of connotations where you could say, okay, so you might designate certain validators who are responsible for managing these blockchains, and you can ensure that it doesn't necessarily mean that all participants will have a full view on the ledger, because that will violate all the trade secrets that I was talking about earlier, right? So all of that can be sort of managed at the sidechain level. And then at the top here, we have what we call a global validator, which is responsible. This sort of acts as the front face to anyone querying the system. And the global validator can go and then pull the relevant data from the sidechains. Now to define the transaction vocabulary, we created 3 kinds of transactions, which pretty much covers most things you want to do in a supply chain. So you have the create transaction, which is mainly to source the individual raw materials, assuming this is something that needs manufacturing. Then as the product in whatever state it is moved from one entity to another, you're essentially transferring ownership to another entity. And that entity may then do something with that item and push forward it to the next entity. So that's captured through this transfer transaction, essentially. And this is multi-signed because 2 entities are involved, right? Whereas if you look at someone sourcing a raw material, it's just uni-signed. And then for items that need to be assembled or manufactured, you have a produce transaction. So this is where the individual raw materials are sort of sourced, combined together. And these produce transactions allow us to sort of link back to the original individual raw materials, right? So you could imagine a product chain to look something like this, right? So this is a mock-up that we've built at that time. So imagine you buy a chocolate bar and you want to know where the milk came from, you want to know where the cocoa came from, right? So you could imagine a system like this where you have all these transactions stored indicating how this particular batch, in this case, was moved around, where it was assembled, and then here you see the individual 2 key ingredients, sort of the provenance for those, right? And of course, you can define what sort of information can actually be viewed by an end user versus, say, an auditor, and so on and so forth. So this system sort of gives you that full flexibility to show things that are relevant to the appropriate person querying. So that was just the base system. I kind of rushed through that because that's kind of a little old and it's fairly straightforward. So once we had this system, we started getting questions. Okay, now how do you trust the data that's written in the blockchain, right? So remember, with supply chains, things are a little different. It's not like cryptocurrency, right, where you're creating the tokens or the coins directly on the blockchain itself, right? So you kind of trust because the mechanisms in which that asset was created, you follow. The assumption is you've followed all the processes, appropriate processes, as defined in the blockchain. So the creation and transfer of bitcoins, for example, is integrated in the proof of work consensus mechanism, right? However, when you're looking at supply chains, we are talking of physical commodities and physical assets, and you're trying to record what has happened with those things in the digital space, right? And this is where you have potential problems because what you might log on the blockchain may not be accurate. And then all you have is a basic garbage in, garbage out problem, right? So you have logged bad information and then it's useless at that point. So that was what got us thinking on how can we start coming up with a way to trust the data that's written in the blockchain in these sort of applications, which are capturing things happening in the physical space. And of course, there is existing work on reputation systems and so on and so forth, but it's not so straightforward to just take that and put this in this context, right? So there are a few other things that we need to look at. We need a way to sort of get multiple viewpoints in order to assess that trust. We need some flexibility because the supply chain entities themselves could be involved in multiple chains of products, if you may. And then, of course, all of this has to be automated and the overheads need to be minimal. So that led us to the second piece of work that we came up with, which we called TrustChain. So the idea here was to come up with a mechanism which sort of allows us to assign reputation and trust scores to the various entities involved in the supply chain. So this goes back to the layered architecture I mentioned. I don't show the storage layer here because that's kind of, I mean, that's just managing the data. So it's not sort of playing a key role here. So it's a 3-layer architecture, and we ensure that it's flexible and granular. So you can actually zoom in and figure out, say, a particular entity, right? So this farmer, what is his reputation in the context of one particular product chain, assuming the farmer's involved in various chains. So it's fairly flexible and granular. Everything is implemented using smart contracts. And there are mechanisms to implement accountability measures like rewards and penalties that we also provide. So this was implemented on Hyperledger Fabric. In fact, the previous work was also implemented. I just didn't show you results for that. So we kind of, all of this is sort of implemented progressively as we keep adding new functions. So this was implemented on Hyperledger, and we demonstrate that the overheads were minimal. So at the data layer, I kind of hinted at this earlier. So we are taking in all sorts of data that we can collect. So typically we expect 3 kinds of data. So you have sensors embedded within the supply chain itself, perhaps even within the product. Now, if you think of a supply chain, right, anytime a product is sort of in whatever state is handed from one entity to another, that is essentially a trade event. And the entity that's selling, so in this case, the primary producer becomes the seller, and then this supplier is going to buy that from the seller, right? So this can be considered to be a trade event. And so in this trade, you could expect that the buyer can sample the item, and then based on certain protocol, they can assign a certain rating to the seller, right? So this can all be sort of written up in a smart contract. And so based on that, we could get certain ratings of the buyers. And then from time to time, you may also get some inputs from some regulatory bodies, right? So what we are proposing is taking all those that information and storing, say, transactions. You either store them directly into the blockchain or you store it off the chain. And I think, I mean, in most cases, you would be storing stuff off the chain, and hashes of that would be written up into the blockchain. And here, as the transactions are coming in, we have 2 kinds of smart contracts that are now going to look at these transactions, and they're going to come up with a reputation score for both the commodity itself and for the entities involved in the product chain. So this information is actually stored in the digital profiles of those supply chain entities and the commodities, and these are managed on the blockchain itself. So these are the 2 key smart contracts that we've designed. So we have what we call a quality contract. So this is coming up with a rating for the product itself, that batch of products. And we have what we call a rating contract. So this is coming up with a rating for individual supply chain participants, right? So the quality contract is mainly taking in inputs from the various sensors. And these quality contract could also be written up in a way to trigger certain immediate warnings. So if, for example, if it's an item that needs to be moved at a particular temperature, you could initiate certain warnings if the temperature bounds are violated. And then for the ratings, we assume you're getting information from the sensors, you're also getting information from the buyers, and you're getting information from the regulators. And all of that is sort of combined together to come up with a rating. So the actual rating can be the exact way you're computing the reputations. There are various ways to do this. So we've used one particular something that we've used in one of our earlier works, which is basically, I mean, this is a very straightforward way to compute a reputation. Essentially, you're putting more emphasis on the current rating. So you have this aging function where with time, the older ratings sort of die away. Right? But you could come up with other ways to compute these ratings. So this allows us, and then you could of course apply certain weightings based on what weight do you want to set for the sensor information, the buyer ratings, and then the regulatory bodies. So all of that can then be combined to come up with a reputation. And you could also take in inputs from other factors. So for example, if say the product was sold on Amazon, if there are certain feedback ratings coming in from Amazon buyers, that could also be factored in here. And you could then compute a final rating for each trader. Then at the top, we have what we call the application layer. So this is where you could sort of implement certain rewards and penalties. So this, depending on how this is implemented, you would pull in you would query the blockchain and obtain the trust scores for the various participants. And then based on certain rules that you have come up with, you would either award them certain rewards or penalties. And then any queries that might be sent, say, by auditors or say by consumers who may want to know certain information about their products are also managed at this application layer. Okay, so in terms of the implementation, so this was all done on Hyperledger Fabric. So this was, we implemented a sort of business network here on Composer at that time for trading amongst 3 supply chain entities. So we assume there's a primary producer, I think a logistics entity, and then a retailer. And in order to test the sort of performance bounds here, we sort of submit transactions and queries to this business network using REST APIs, and all the benchmarking was done in Caliper. And we used a particular network model there. I think it was a solo orderer node and 2 endorsing peers from separate organizations, all in one communication channel. Now, of course, the numbers here are not that, the absolute numbers are not important because this at that time this was done, I think, just on a high performance desktop. So the numbers are not so much representative. I mean, if you scale this up to higher performance machines, you would get higher numbers. But the point here was to compare the overheads, right? So here the blue bar indicates a system which we call a baseline system, which is essentially just like ProductChain, that's just managing the supply chain, but it doesn't have all these add-ons for the reputation and trust and so on and so forth. So the key point here was to just show that the overheads that we introduce are fairly minimal. So this here shows you the difference in latency, and this here shows you that there's a slight drop in throughput. Right? So this is for trade transactions, and then this is for create transactions. So the main message again is the overheads are minimal of this approach.
Salil, let me make a question.
Yeah, sure.
So if you can go to the previous slide.
Yep.
So as well increase the second graph, trade transaction throughput. So as you are increasing the transaction send rate, I see that the throughput is initially increasing and it is dropping. So which specific reason for that?
Oh yeah, good point. I forgot to mention. So this is essentially the network got saturated at that point. And so yeah, if you push further, it just kind of goes into collapse. That's the reason. But yeah, I think, I mean, you could get better numbers certainly on a higher performance machine.
So what was the typical network size?
So I think what we did here was, it was a fairly simple network, one of the standard network models in Caliper. I think I forgot, I don't have the notes here, but I think it's a solo orderer node and I think 2 endorsing peers. So it's a fairly small network, essentially.
Okay.
Yeah.
Thanks.
No worries. Okay. Yeah. So then in the remaining part of the talk, I'll focus a bit on some of the privacy work that we've done. Right. So this is a little newer work that's done in the last year or so. So in general, there's this trade-off, right? I mean, you want things visible, you want everything visible. That gives us traceability. But again, here we are talking of businesses. They want to make money. They may not necessarily want to reveal everything, right? So there's this sort of tension between privacy and traceability, right? So this is something we've found when we talk to a lot of businesses, right? If they're interested in sort of looking at blockchain, that this is something that always comes up, right? They worry about who can read their data that's on the blockchain. So if you think about it, there are two aspects of privacy here. One is, of course, the data itself. You do not necessarily want to reveal everything, but at the same time, you want to be able to provide provenance and traceability, right? Because otherwise you're defeating the whole purpose of this using the blockchain in the first place. The second aspect is how do you hide the identity? So this has to do with what's called the linking attack, right? So even if you're using pseudonyms on a blockchain, people have shown that you could actually link transactions together. And this can again be a problem in the context of trade because that gives you a lot more information about one particular trader, right? So we need to be mindful of those, and we need to come up with solutions which can help address those two issues. So this is what we've done in these two pieces of work. The first work I'll talk about is PrivChain, that's focused on hiding the data, and the second one talks of the identity problem. So this was just accepted a few days ago and will be presented at the IEEE Blockchain Conference next month. So here we are trying to solve the problem, the data problem, right? So we want the trader to still use the blockchain, still provide provenance, but we do not necessarily want to share all the data, right? So the natural fit for that is, of course, zero knowledge proofs. So here we kind of show one way to use zero knowledge proofs to provide provenance, but provide privacy, but still provide provenance. Then, of course, all of this was implemented using smart contracts. And what we also did was we came up with a way to implement a incentive mechanism. That way, because as you'll see, some of this computation requires some extra work from the participants. And then the question is, why would they do it, right? So to sort of incentivize the farmers, say, to participate, we've sort of included an incentive mechanism that enforces an instant reward for participating and following the sort of right protocols. And then this was all implemented again on Hyperledger, and we do some benchmarking. So yeah, I mean, very quickly, the basics that we use, of course, are zero knowledge proofs, which allow us to, in which you have this prover and you have the verifier, right? So the prover can attest to a verifier that some secret information is true, but they do not necessarily reveal all the details about the secret, right? So this is a sort of, there are, of course, various instantiations of this, and we use one particular one here. And then for the other aspect, for the incentive, for implementing the incentives, we use PIDUS and commitment. So this is essentially a non-interactive secret sharing scheme, right? So this is the high-level view of the system. And as an example, we use wine. So let's say we are talking of someone sort of bottling the wine, winemaker, and they're sourcing their grapes from various farms, right? So the idea here is you want to, so in Australia, for example, there are various wine regions. So people always, I mean, people who sort of are interested in wine, they have their preferences, right, of what region wine comes from and what they attach some sort of um, connotation to that, right? So wine coming from X region should taste like that, and so on and so forth. So there's this whole marketing, right, that goes along that, okay, this wine comes from this region. Now, what we are saying is, okay, you still want to ascertain that the wine came from that particular region, but you may not necessarily want to reveal the precise farms that the grapes were sourced from, because that may be a trade secret, right? So that's how we sort of set the problem, that you want entities to be able to check and confirm that the wine came from a particular region, but not necessarily know the precise locations of the farm where the grapes came from. So in that context, this is showing the high-level overview. So very quickly, there's a first step to just set up certain parameters that are needed for the proof computations. Then we have all the supply chain entities, in this case, the grape producer, who is sort of sourcing the grapes from the grape farm. They will generate a zero knowledge range proof for the location whenever they're registering a new batch of grapes using that create transaction. And while doing that, they also generate a commitment for a certain pre-agreed incentive using the trade transaction. Then this gets sent to the blockchain. There's a smart contract here that verifies the location, and assuming the location proof is correct, they will register the grape commodity on the blockchain and along with the verified region. And it will also trigger a request to the bank to release the incentive payment to that grape producer. Then the supply chain entity that's assembling the wine, they will sort of imprint a QR code onto the wine, and then a consumer can scan that label, which will generate a query to the blockchain, to the smart contract, which will then again verify the proof of location, and then the consumer can get a confirmation that yes, this wine indeed came from that particular region. So that's sort of the big picture there. So a little more details here. So this is showing you the setup phase. So there's an initial registration process. This is just some basic parameters, right? So the verification key, the proving key, and some other parameters that are needed for the zero knowledge computation. Now, one thing to note is what we've done is we kind of, I mean, if you look at latitude, longitude, right, there are millions of latitude, longitudes, precise locations, right? So computing these location proofs on individual GPS coordinates is a little impractical, and checking them can take forever. So what we propose is, which is quite standard in sort of systems like this. So rather than sort of assuming individual latitude, longitudes, you break up space, the sort of geographical region of the Earth, into grids. So there's this military reference grid system that's used. So this is essentially just you divide up geographical regions into squares of X meters by X meters. So this could be, say, 1 kilometer by 1 kilometer or whatever size you want. And then we are just computing the proofs on that grid. So you could take any farm, you could indicate that this farm belongs to this particular grid, and then you're computing the location proofs on those grids rather than individual latitudes and longitudes. So that allows us to scale this up. So the proof generation is executed off the chain. This is not on the chain itself. So it's fairly straightforward here. So this should actually just be XY. Sorry, I didn't notice that. So this is the latitude, longitude that's coming in, certain public inputs for the authorized range. This results in the computation of the proof, which is signed by the proving key. And then down here is the commitment. So the assumption is this incentive amount is already sort of negotiated, right? And then certain public inputs are used to do the commitment. This is the actual create transaction where the location information is noted. This is where the producer sends the proof and the commitment that was shown on the previous slide. This smart contract is then used to verify that because here we assume we have pre-computed this on those grids. So that allows us to quickly verify if the location is correct. If it is correct, then a trade transaction is recorded on the blockchain, indicating that this information essentially. And this payment request is also sent to the bank. The bank will, which is shown here, and the bank will then pay the grape producer the incentive amount. Okay, now here we kind of, this is for the trade flow protection, right? So you still want to do the provenance, but you may not necessarily want to reveal all the identifiers of where the grape actually came from, right? So this, what we do is we use some encryption to hide the IDs of the original transactions that recorded the the create transactions for the individual batches of grapes. And we assume this is encrypted using a symmetric key. This does create the problem of how do you share the key, but we assume that's done in some manner off the chain, right? Whereby you can sort of arrange a way to share this key with whoever needs to check these locations. And then these are the regions, and this is then signed by the buyer. So this allows us to sort of check those locations. Now, in terms of implementation, this was just done on Hyperledger Fabric, and as before, we used Caliper for all the benchmarking. In this case, the network was two organizations depicting a grape producer and a wine producer. So that's the grape producer is the seller, the wine producer is the buyer. And we assume that the network consists of two peer nodes, one orderer, so using Solo, and then a database and a certification authority. So for implementation of the zero knowledge proof and the Pedersen commitment, there's this ING bank repository, which is an open source library. So that was used to do all the proof computations and commitments. The verification, of course, is done on the chain. The generation of all the proofs are done off the chain. So here you see the overheads of using those proofs. So of course, the setup takes a little bit of time, though again, it's not that high. This is milliseconds, so we are talking of about a little over a second. The proof generation takes less than 1 second. This is the trade transaction with registering that with the zero knowledge range proof. And this is showing you what the time for the trade transaction without using zero knowledge range proof. So yes, there's certainly a sort of 5-fold increase, but then again, if you look at the absolute numbers, this is not a lot. This is just taking 1 second. This here shows you the time needed for registering the final product. So again, this is the baseline, and this is with our mechanism with the privacy part. So yes, there's a increase, but again, we are talking of really 70 milliseconds of increase, right? Down here, we show the sort of how high can you go in terms of how many transactions can the system handle, right? So the throughput. So yes, we can get a fairly high throughput, about 150. Again, then we hit the saturation, so the throughput starts to drop, and the latency is still fairly low. So again, this is kind of, the absolute numbers are kind of relative to the hardware, but this is just an indication that even in a simple lab setting, we were able to get reasonable numbers for this. Okay, I know I'm kind of running out of time, but I'll try to be quick here. So this is the last piece of work that we did in this sequence that I'm presenting. So this focuses on decoupling the identities, right? So we still want, we still want all these functions, but we do not want anyone who has access to the blockchain to be able to link transactions for a particular participant, because that can give them a lot more information about how that participant is behaving in the context of supply chains. Right. So what we are essentially doing is providing a mechanism where we decouple the trade events using decentralized identities. So the way we do this is we create two separate ledgers. So we create what we call a identity management ledger, IDML, for managing the decentralized IDs. And then we have a transaction management ledger, which is very similar to what we have been seeing so far. So this is the traditional ledger I've been talking about. We use zero knowledge proofs on these credentials. So this allows the traders to prove to the entity managing the TML that they are authorized without necessarily revealing their actual credentials. And one thing that we do is we still want to be able to provide traceability, right? So it's not like we don't want anyone to be able to link the transactions. We just don't want any arbitrary person to be able to link the transaction. So in other words, the trader gets a say on deciding, okay, this particular entity can go ahead and link my transactions. And to do that, we come up with dynamic access rules. So we are basically using a token mechanism. So the trader can issue tokens to someone, and then the person, assuming they have the tokens, can then go and collate and link the transactions to be able to do the traceability verification. So at the high level, what we are doing is we are using this notion of self-sovereign identities. So the idea that you can you're giving the ownership of creating identities to the actual individual, right? So they can create multiple identities and manage this using a wallet, a digital wallet. So there's this whole notion of self-sovereign identity, or SSI, that has been proposed for this. So at the high level, this is what we are doing essentially. So the traders go through a onboarding and credentialing process. They can create as many identities, or DIDs as they are called, decentralized IDs, as they want on the IDML. In order to trade, they first need to join. And while proving to the TML that they are registered here and they are a valid user, they make use of zero knowledge proofs on the credentials. So that way they are not necessarily revealing who they are, just that they have been registered on the IDML. Then they can use their multiple DIDs on the transaction on the TML and transact as normal. They could even change the ID for each transaction if they wanted to. Now at a later point, if there's someone who wants to do the sort of verification, right, do the provenance. So that means they need to link up transactions of a trader. They would ask the trader, they would obtain certain access tokens. And then the requester would query this QSM. This is a smart contract that we designed, a query smart contract, which will take the tokens. It will then verify those tokens and then fetch the appropriate transactions from TML, link them, and provide the information that's requested, right, without revealing the trader's credentials or DIDs. So this is still done in a privacy-preserving manner. I think I'll skip the slides here because I think I've kind of run out of time. I may just show you very quickly the evaluation. So this is sort of showing you the various processes that need to be done. So this is showing you how long it takes for a trader to register on the TML and the various components of that. So that's about 7. I think this should be seconds. I think there was, yeah. I think I made a mistake. I've used different graphs. In any case, these numbers are fairly small still, right? So this is the registration process. This is for trading a commodity. That's for generating a token for trading the commodity, and then now validating the token and returning the result. So these numbers are still fairly small. And again, these numbers could be improved on a higher performance machine. And then as before, we look at the transaction, how many transactions can the system handle for various types of transactions. And again, we get fairly reasonable numbers here. So for example, here to register a commodity, we can go almost up to 400 transactions, slightly higher here for trading a commodity. So yeah, I think I'll leave it at that. Yeah, maybe just a few words on what still needs to be done. So of course, we've just been scratching the surface here. There's lots more work yet to be done. So interoperability is a sort of hot topic these days, not just in the context of supply chains, but in general in blockchains, right? So there's this notion of you might have various blockchains managing various aspects of the supply chain. And so we need ways for these blockchains to be able to talk to each other, right? So that's a very hot and relevant topic for research. To address the garbage in, garbage out problem, again, we showed one way to do it, but clearly there could be other ways. People are looking at smart biological fingerprints, for example, for doing all the quality verifications. There's a lot of work yet to be done on incentives and how do you manage them, particularly making sure that the incentives are flowing back to the farmers and small scale suppliers who always end up losing out in these big supply chains. There's issues around governance and regulation, which need to be addressed. There's also this very interesting and relevant issue of sustainability, right? So I think people are now realizing we need to start quantifying the carbon footprint of various things. And of course, supply chains are sort of generating a lot of carbon. So how do we quantify that? Given that we're recording all this information of the blockchain, it should perhaps help us come up with some ways to quantify this and promote more sustainable practices. Then, of course, on the privacy side, we showed a couple of things, right? Now, of course, we only looked at 2 specific sort of ways to do it. There are still a lot of explorations to be done in that space as well. Yeah, I think I'll conclude here. I'll briefly mention the book that we have out, which is something you might be interested in looking up. So again, thanks for the opportunity, and happy to take questions and comments.
Yeah, thanks, Salil, for the detailed talk. So we can take up questions. So any question from the audience? So Salil, kind of a broad query, like say for example, whenever we are talking about this supply chain management at using blockchain. So one of the major issues is possibly like so there are different elements of a supply chain, starting from the suppliers, the end users at different levels. So for a practical deployment of such a system at a large scale, so I think it is always difficult to involve all the stakeholders to have some kind of or means have their own computing resource where they can set up a blockchain node, and possibly that is one of the major challenges behind deployment of such kind of systems in practice.
Yeah.
So what do you think about that, or what is your experience about deploying such kind of blockchain-based environment in a practical supply chain management use case.
Yeah, I think that's a good problem, a good point you make, Sandeep. And we've had a lot of discussions with industry partners, and yeah, in the end, some of them start asking this, right? I mean, the investment, I mean, what are they? Because it's a lot of investment we kind of expect them to do, and the gains are not very clear. So I think, I mean, there are systems now coming up, this whole concept of blockchain as a service. So perhaps there's the possibility of using some of that. Um, and yeah, I mean, to begin with, we are saying, okay, at least start looking at some of the key things that are relevant to the, say, traceability problem. Let's at least get a version 1, version 0, let's say, going. And then once you have a little more insight into what other things you want to sort of register on the blockchain, we can start expanding that. So sort of doing a layered approach is been trying to pitch.
Right. Okay. So any other query?
So I have actually from again high-level questions. So fantastic work, Salil. I mean, just really just a lot of work went into this. What I was wondering about the deployment, like you actually come up with the very real example of how supply chains are affecting our lives. So, what do you think the key barriers, based on this work, what do you think the key barriers of deploying this blockchain in supply chain in real world? Is it mostly the stakeholders, or there are technical challenges that you're working on, or the community is working on that?
Yeah, Maina, thanks. Good question. So yeah, I mean, we see a lot of so a lot of questions we get from industry partners. So we've been working with a few. A lot of the issues are not technical at this stage, I must say, in terms of getting this to market, right? So for example, we've got a partner whose main export is into China, right? So a lot of his questions are around governance and this cross-border trade and all that. So that's a little beyond computer scientists, our domain, right? So we have kind of so these sort of things I mean, we can if we know what to implement in the smart contracts, we can do that. But what exactly should those agreements be? What should be the governance structures is way out of scope for us to manage. The other end of the spectrum is if you go to small scale sort of farmers and at that level small scale manufacturers, they're kind of just with supply chains we found, I mean, the amount of digitization is so poor that they don't even have systems that can easily tap into this, right? So we can I mean, they don't even have proper ERP systems or anything like that where we can say, okay, we just want to add this. So some way to sort of interface what we are doing with what they already have, and that itself is a challenge. So yeah, some of this is a lot of this we find is engineering and then governance, policy, stuff like that.
Thank you. So just to actually double down on that, and for the second problem, if there are no supply chain available, then I mean, we cannot really help. I mean, that is not really as commerce rather than computer science per se, right? I mean, to creating that, there is no pipeline that we can implement.
Yeah.
But for the governance one, what I was wondering about the auditing infrastructures, which actually comes under the purview of computer science in terms of like, building some systems where both, which actually aligns with both the country's trade laws, like, if you don't get the permission from two parties at least, and two parties have to be in two different geolocations, you cannot really ship a product, for example. I that is extremely interesting, given that I think that this, like, aligning the systems with country's law produce additional engineering challenges, and like opens up way to make new systems, which is some of them are totally out of control, right? I mean, it's like we just don't want people to send X from China to India, or we want to send from Russia. You cannot do anything with it. However, if they ask like without special permission from these commissions, like two different parties within two different geolocations, you cannot really sign this smart contract, and this particular product has to be shipped to this particular line only. Like, there has to be some specific line. That might be something interesting. So thanks for the thought.
Yeah, thanks, Panna.
Any other query? Okay, so if there are no more queries, then we can close the talk. So thanks, Salil, for accepting our invitation and giving a talk on a very interesting problem. So we have to, in a current situation, we have to organize the talk virtually, but hopefully we'll be able to have you sometime in IIT Kharagpur. We'll be happy to host you. So just let us know whenever you are in India. We'll be happy to have you.
Certainly will. Thanks so much, Sandeep. And yeah, hope to catch up in person.
Yeah.